These are the notes for AP Calculus on the topic of implicit differentiation. So implicit differentiation is used when you're taking the derivative of things that are not functions. So you can see we've got the equation x squared plus y squared equals 13, gives us the circle. And you can see it's not a function because it doesn't pass the vertical line test. When you draw a vertical line, it goes through the graph more than once in several places. But you can still find tangent lines and derivatives of this graph, even though it's not a function. So what you do here when you have something that's not a function, you can notice you can tell that it's not solved for y, is you take the derivative of the whole equation, and the way you write that is with brackets around it, d over dx. Remember, that's how our derivative formulas are written. And the same rules for derivatives apply, except when you take the derivative of x squared, you'd write 2x, and to indicate what variable it is, since it's not a function, you'd write dx right next to that. And then when you take the derivative of y squared, that would be 2y, and since the variable is y, you put dy next to that, indicating the variable is y, equals the derivative of 13 is 0, and 13 is just a constant. And then remember, we're trying to find dy dx. So to get the dy dx in there, your next step would be to divide everything by dx. So you can see when you do that, the dx is here reduced out, so all you're left with is 2x. And then the way we can group this, there's a dy dx right there. So we can write this plus 2y, and then group that as dy dx. Equals 0 divided by dx is just 0. The difference here is when this is a function, your dy dx is already by itself, but if you use implicit differentiation for something that's not a function, you're going to need to isolate the dy dx to solve for it. So the first step from there, you subtract the 2x, so you have negative 2x on this side, equals 2y times dy dx. And then finally, to isolate the dy dx, you would divide by 2y. So we get dy dx, our derivative, equals, notice the 2's reduced out there. So you just have negative x over y. So that would be our derivative of the circle. Notice what's different about the derivative here. Unlike functions, our derivative has both x and y, not just x. And that's necessary when we look at the second part of this. It says find the slope of the graph at the point 2, 3. So here's the point 2, 3 on our graph. Let's find the slope of the tangent line of the slope of the graph right there. So now all you have to do is substitute that into the derivative. So we're evaluating the derivative right at the point 2, 3. So you write a vertical line and show that you're plugging in x equals 2 and y equals 3. And when we do that, we get x is 2, so negative 2 over y is 3. So we get negative 2/3. So what we just found is the slope of the tangent line right here is exactly negative 2/3. Now, to see why it's necessary to plug in both x and y in the derivative, if you just plugged in 2 for x, if your derivative only had x in it, well, x was 2, you wouldn't know whether you're talking about this point here at 2, 3 or this point down here at 2, negative 3. So that's why you're going to see the derivatives here have both x and y in it, because there's more than one point with the same x coordinate on things that are not functions. Now, you can find all the derivatives implicitly this way. When you take the derivative of x term, put dx. When you take the derivative of y term, put dy, and then divide by dx. But if you want to save yourself a couple of steps here, to go directly from here to right here, notice what's happening is that every time you take the derivative of an x term, when you put dx, eventually you're going to divide by dx. So the dx's are going to cancel out anyway. So you can just take the derivative of x squared as 2x. However, every time you take the derivative of a y term, a variable that doesn't match up with the x here, you're going to multiply by dy, but it's going to get divided by dx, so it's essentially going to get multiplied by dy dx. So to go from here to here, when you take the derivative of an x term, you'll just take the derivative like normal. When you take the derivative of a y term, you just have to remember to multiply it by dy dx. So that's the shortcut I'm going to use on the rest of the examples on the notes. So this one says find dy dx, the derivative. So again, you can see the x's and y's are mixed up here. This is not a function. To take the derivative here of x sine of y, well, we have x times the sine of y. So all the same rules for derivatives still apply. We're going to have to use the product rule on that. Since we have x times the sine of y. So the pattern of the product rule says we take the derivative of the first one. The derivative of x is 1. And since that's x, we don't need dx because it's just going to cancel out anyway. Times the second one, sine of y as it is. We don't put dy dx there because we didn't take its derivative. We just left it alone. And then after you take the derivative of the first one times the second one as it is, then the product rule says you have plus the first one as it is, which is x, times the derivative of the second one. Derivative of sine of y is cosine of y. And that's where we took the derivative of a y term. So that's where we're going to need to multiply it by dy dx. Equals derivative of 3y would be 3. Again, we took the derivative of a y term, so we need to multiply it by dy dx. And then to take the derivative of cosine of 2x, you can see we've got a function inside there. With parentheses around, you can see there's 2x inside of cosine. So that's what we're going to require using the chain rule. Okay, so start on the outside. The derivative of cosine is negative sine. And the function inside 2x stays the same. But then we use the chain rule multiplied by the derivative of 2x, which is 2. And there it's a derivative of x term, so we don't need dy dx. So notice what's different about this one, we've got more than one dy dx expression. We've got one on the left side of the equation and one on the right hand side of the equation. So the way you're going to solve for dy dx is you're going to group all the terms that have dy dx on one side of the equation and all the terms that don't have dy dx on the other side of the equation. So it can be either side. So let's say we move all the dy dx terms to the left. So I'll leave this x cosine of y on the left times dy dx. And I'll subtract this 3 dy dx, so it's over on the left-hand side. So those are the terms that do have dy dx equals, and all the terms that don't have dy dx you want on the other side. So I'm going to subtract the sine of y, so it'll be negative sine y. And then just leave this term over here, just bring the 2 out in front, so that's negative 2 sine of 2x. Now the reason why that's helpful is that helps us to isolate the dy dx because now we can factor it out. It's like a GCF. So you can factor out the dy dx. And then what you have left in parentheses there is x cosine of y, that's what's left of the first term. And negative 3 is what's left of the second term. And on the other side we still have negative sine of y minus 2 sine of 2x. And then finally, to isolate the dy dx, you can see we can just divide by what it's multiplied by. Divide by this x cosine of y minus 3. And then to balance it out, you've got to divide the other side by x cosine of y minus 3. So our derivative, dy dx, would be negative sine of y minus 2 sine of 2x divided by x cosine of y minus 3. And you can look and see if anything simplifies, but in order for something to simplify, you have to be able to factor it out, get the numerator and denominator factored formula. And really all you can factor out is a negative, and there's nothing really factored on the denominator, so nothing reduces in this case. Notice again our derivative has both x and y, since it's not a function. Look at the next one. This one again says find dy dx. We've got sine of xy equals x plus y to the fourth. So again, it's not a function, so let's take the derivative implicitly, take the derivative of the whole equation. This one's a little bit more complicated because we've got the sine of xy. So first of all, because we have a function inside, we need to use the chain rule. We've got xy inside of sine. So let's start on the outside. Let's start on the outside. The derivative of sine of xy would be cosine of xy. And there we don't put dy dx yet because we only do that when we take the derivative of just a y term. This has both x and y, so that'll come into play later. So now the chain rule says we have to multiply by the derivative of the inside, but notice the inside function is x times y. So when you take the derivative of the inside, that requires using the product rule. So we have x times y. So this whole cosine of xy gets multiplied by the derivative of the inside. That's what the chain rule says. So we put parentheses there. Now let's take the derivative of the inside using the product rule. So the derivative of x is 1 times the second one y as it is, then plus the first one as it is x times the derivative of y is 1, but that's the derivative of a y term, so that's where we need dy dx. So notice we took the derivative of the outside, derivative of sine is cosine of xy, times the derivative of the inside using the product rule. Now let's look at the right side of the equation. On the right side, also we need the chain rule because we have a function inside, it's x plus y. However, it's not quite as complicated because it's not going to involve the product rule. So on the outside here, we would just be using the power rule. So bring the 4 out in front. X plus y stays the same inside. And now to the third, reduce the exponent by 1. So that's the derivative of the outside. But the chain rule says we have to multiply again by the derivative of the inside. But this was a little simpler because they're just added together, not multiplied. So we don't have to use the product rule. When they're added or subtracted, we can just take the derivative of each one separately. So the derivative of x, which is 1, plus the derivative of y is also 1, but that's the derivative of y term, so we need to multiply by dy dx. Now, this one, if you try to get the dy dx's all on one side at this point, it's a little difficult because they're in these expressions with parentheses. So to get rid of those parentheses, you can just distribute it out. So if we distribute out the cosine xy times y, that'll be y cosine of xy, and then distribute it cosine of xy times x dy dx, so plus x cosine of xy times dy dx equals, then we can do a similar thing on the other side, distribute out this 4x plus y cubed times the 1 is just 4x plus y cubed, and then 4x plus y cubed times dy dx, so we have plus 4x plus y cubed times dy dx. Now there's no more big parentheses those dy dx's are in, so now we can use a similar strategy to the previous problem, where we get all the terms that have dy dx on one side, all the terms that don't have dy dx on the other side. So again, let's say we have them on the left here. So I can leave this term over here. I'll leave the x cosine of xy times dy dx, and then subtract over the 4 x plus y cubed dy dx on the left, and then on the right side, we'll leave all the terms that don't have dy dx. So we'll leave this 4 plus x plus y cubed, and then subtract the y cosine of xy. So now all the terms that don't have dy dx are on the right. So now, what again that enables us to do to solve for dy dx, to isolate it, we can now factor it out like a GCF. So we factor it out, we're left with x cosine of xy, and then minus 4x plus y cubed equals, this side stays the same for now, 4x plus y cubed minus y cosine of xy. And finally, to solve for dy dx, you just divide by this whole expression in parentheses. So our derivative, dy dx, would be 4x plus y cubed minus y cosine of xy, all divided by x cosine of xy minus 4x plus y cubed. And see if anything cancels again. It would have to be something we could factor out, the numerator number, so there isn't. I know it's tempting to cancel out these 4x plus y cubes, but you can't do that because it's not in factored form. So that's as simple as it's going to get. Now let's think about what would happen if instead we took all the dy dx's to the right side and moved all the terms that don't have dy dx to the other side. Well, if we had done that, then basically every term would be on the opposite side of the equation, meaning every term would have the opposite sign. So your final answer would have a negative, and this term would be negative, this term would be positive, this term would be negative, and this term would be positive. Which is really the same answer because it's just like multiplying the numerator and denominator by -1. So for e-response, that's not really important because either way would be correct. What's important is multiple choice questions where if you're trying to match up your answer to the correct multiple choice answer. If you don't see your answer there, it might not be that you're doing it wrong, it might just be that they move the dy dx to the other side and every term is the opposite sign. So just keep that in mind. Now let's take a look at finding the second derivative. Remember, that's what this means here. And it says in terms of x and y. Well, we have this equation before we can find the second derivative. We need the first derivative. So let's start there. The derivative with respect to x, the derivative of 2x to the fifth is 10x to the fourth. The next term, so we don't need anything else, equals. Now when you take the derivative of xy, that's going to require the product rule. X times y. So I take the derivative of x, which is 1, times y as it is, plus, first one as it is x, times the derivative of y is 1, but that's where we need the derivative of y term, dy dx. And then the derivative of constant 5 by itself is 0. So this time it's a little simpler to get it for sure, because there's only one dy dx. It's easier to isolate. All I have to do is subtract the y over. So we get 10x to the fourth minus y equals x times dy dx. And then last step to solve for x, you just dy dx, you just divide by x. So we get our first derivative. Dy dx is 10 x to the fourth minus y divided by x. So that's our first derivative. But we want to find the second derivative here, so we have to take the derivative of that. So you can put brackets around this just like we did the original equation to take the derivative of that. And you can see, since we have 10x to the fourth minus y divided by x, that's going to require using the quotient rule. So we take the derivative of the first derivative, that's going to be the second derivative, which we write as d squared y dx squared. And remember the quotient rules, the pattern is we take the derivative of the numerator, and since they're just subtracted, we can take the derivative of each one separately. So that's going to be 40x cubed minus the derivative of y is 1, but that's where we took the derivative of y term, so we're going to need dy dx. And put that whole thing in parentheses, because that's just the derivative of the numerator, and then the quotient rule says you take the derivative of the numerator times the denominator as it is, which is just x, and then minus the numerator as it is, 10x to the fourth minus y, in parentheses, times the derivative of the denominator, the derivative of x is just 1. All divided by the denominator squared, so x squared. And then we can start to simplify this. So here you can distribute out the x as both of these, so that would make it 40x to the fourth minus x times dy dx. And here if you just distribute out the negative one, that would be negative 10x to the fourth and positive y over x squared. Now we've got some like terms on the numerator. We've got 40x to the fourth minus 10x to the fourth. So you can find this to be 30x to the fourth. So our second derivative equals 30x to the fourth minus x times dy dx plus y all over x squared. However, notice our answer said, the problem said to find the second derivative in terms of x and y. So take a look. Is this in terms of x and y right now? Well, almost. There are x's and y's, but notice it's not in terms of x and y because we also have, in addition to x and y, we have a dy dx in there. So to get rid of the dy dx, all you have to do is, well, that dy dx, that represents the first derivative. And remember, we already found the first derivative before we found the second derivative. It's right here. So all you have to do is substitute that in to get it entirely in terms of x and y. So we'll have the second derivative, 30x to the fourth minus x times our dy dx was 10x to the fourth minus y over x, and plus y, divided by x squared. And you can see when you multiply that out, the x's are going to reduce out. And then you can just distribute the negative times both of those. So our second derivative here is 30x to the fourth. Distribute the negative, that's negative 10x to the fourth, and positive y, and plus y, divided by x squared. And we just have a couple more like terms there. So our second derivative, 30x to the fourth minus 10x to the fourth, is 20x to the fourth. Y plus y, 2y, divided by x squared. So there's our second derivative in terms of x and y. Yeah, there's nothing that simplifies because you could factor out a 2 here, but there's nothing to reduce it with on the denominator anyway. Finally, on the first part of these notes, let's take a look at the equation of the tangent line at the indicated point. So remember, the two things we need for writing the tangent line are the point of tangent and the slope. But in this case, if we said at the indicated point, well, we're already given our point of tangency right here, negative 1, 2. So all we need to find in order to write the tangent line is the slope, and the slope comes from the derivative. So we just take the derivative of our equation here. So the derivative of x cubed is 3x squared. The derivative of x term, it matches up with the variable out here, so we don't need anything else. Plus, now on the 2x times y, that's where you have to use the product rule. So if we treat the first one as 2x, the second one is y. The derivative of the first one, the derivative of 2x is 2, times the second one as it is y. And then plus the first one as it is 2x, times the derivative of y is 1. But there we took the derivative of a y term, so that's where we're going to need dy dx. And then plus we have the derivative of y cubed, so that's 3y squared. Again, we took the derivative of y term, so you multiply that by dy dx. Equals the derivative of 3 by itself is 0. So now we want all the terms that have dy dx on one side, all the terms that don't have dy dx on the other side, solve for it. But notice the two terms that have dy dx are already on the left side. So all we have to do is move the other terms that don't have dy dx to the right side. So we can subtract the 3x squared and subtract the 2y over to the right. And once we do that, once these terms are gone, the remaining terms have dy dx. So we can now factor the dy dx out of those two terms. So we're left with is 2x is left of the first term, and then plus 3y squared is left of the second term. And then solve for dy dx, you would just divide by 2x plus 3y squared. So our derivative would be negative 3x squared minus 2y over 2x plus 3y squared. Well, we're not done yet because here we're going to use this to find, that gives you the slope at any point on the graph. We want it specifically at our point of tangency. So now we want to substitute in our specific x and y coordinates. So the derivative specifically when x equals -1 and y equals 2 would be -3. For x, we're going to plug in -1, so -1 squared minus 2 times y is 2 over 2 times x is -1 plus 3 times y is 2. 2 squared. And let's go ahead and evaluate this. Well, -1 squared is 1 times -3 gives you -3. -2 times 2 is -4 over 2 times -1, -2. And here we've got 2 squared is 4 times 3 gives you 12. Combine those, -3 minus 4 is -7. Over -2 plus 12 gives you 10. So that's the slope of the tangent line. So now we have the slope and our point of tangency, so now we can write down our tangent line. Would be y minus the y coordinate, which is 2, equals the slope, which is -7/10 times x minus the x coordinate, which is -1, so that becomes x plus 1. And that concludes the first part of the notes for AP Calculus on the topic of implicit differentiation.